Hello, welcome to the quantum mechanics class. Today we will discuss particle in a one-dimensional, the potential well. So the objective of this particular program is first to understand the behavior of quantum particle in a infinite potential well. Then what will be the wave function for the particle? Wave function for the quantum particle. Then energy spectrum of the quantum particle. Then the probability distribution of particle inside the potential well. Inside the potential well. These are the objectives to perform the calculation for this particular problem. So let's consider this is the one-dimensional infinite potential well. One boundary at x equal to 0 and then second boundary is at x equal to a. Then this is the potential, the axis, and then this is x-axis, which is representing the motion of particle. So let's consider the particle is here. This is the quantum particle. So definitely we will describe this particle by a matter wave, and then the wave function for that wave is we assume it is the psi x. Okay, the psi x is the associated wave function to this quantum particle. Particle is free inside the box, so the potential energy of the particle is 0 inside the potential the well, and then at x equal to 0 and x equal to a, the potential is infinite here because the height of the potential, this boundary is very large. So we can assume this is the infinite potential boundaries here. So now the first object is that what is the wave function here for this particle, and then what is the energy of the particle which is confined in the potential well here. But we know that the potential energy is the 0 in the region okay. So in this region the particle is freely moving, so that's why we consider the potential energy is the 0. So for getting the wave function, so we will use the Schrodinger time independent one-dimensional equation. So the Schrodinger equation for the particle, so Vx psi x equal E psi x. Okay, so let's say this is the equation number 1, or we can also write just rearrange this equation. So we will get and 2m h cross square E minus Vx psi x equal 0. And since particle is confined in this potential, this region, so the Vx equal to 0 in this region. So the equation will be plus 2m h cross square is psi x equal to 0. Okay, so let's say the equation number 2 here. So this is the equation number 2, and then so let's assume the v let's assume that 2m h cross e is the k square. Okay, so when we use this value in the equation 2, then the Schrodinger equation will be plus k square psi x equal 0. So this is the second order. Homogeneous equation. The general solution of equation 3 will be a sin kx plus b cos kx. Okay, so let's say this is equation number 4. So this is general solution. Now here a and b are the constant. So for getting the value of the a and b, we have to use the boundary conditions. So we have the two boundary conditions. The wave function is the 0 at x equal to 0, and then wave function is the 0 at x equal to a. Because at x equal to 0 and at x equal to a, the probability of finding the particle is the 0 here. Also, the probability of finding the particle 0 here as well as 0 here outside this region. Okay, so the probability density is psi star psi. So since the p is 0, it means the wave function is the 0 at that particular position. Okay, that's why we are taking the wave function is 0 at x equal to 0, because it is the infinite boundary, and at x equal to a we have the infinite boundary. So now if I use these both boundary condition in equation 4, so first boundary condition is at x equal to 0 psi x equal to 0. Okay, wave function will be 0. So if I use this condition in equation 4, then I will get psi a sin 0 b cos 0, and this is the 0, and then sin 0 is the 0 and cos 0 is the 1. Okay, so I will get the 0 here and then b here, so it will gives you b equal 0. Okay, let's say equation number 5 here. So if I use this b in the equation 4, use equation 5 in equation 4, we get the psi x equal a sin kx. So this is equation number 6. Okay, now second boundary condition, at x equal to a, the wave function is again 0. Okay, so use the boundary condition in equation 4 and use condition in equation 4. What I will get? X equal to A, then A sin KA. Okay, but this value is the 0. So I will get the 0 equal A sin KA, or we can write in this way, the A sin KA equal 0. Let's say equation number 7. Okay, so this is equation number 7. And so from the equation number 7, we know that the A sin KA equal 0. It means there are three conditions. One condition is, let's say A is, it means if A equal 0 and then sin KA equal non-zero, then I will get A sin K equal 0. And then second, if A is non-zero and then sin K equal 0. And then if both are 0, A sin equal to 0 and then sin Ka equal to 0. Okay, so in these four these conditions, I will get A sin K equal to 0. Okay, but if I consider A equal 0 and then sin Ka equal non-zero. Okay, so if the A equal 0, then if use A equal 0 in equation 6, this is the equation 6. So what is the psi? Equation 6 is this one, A sin Ax. Okay, so if A equal 0, then I will get the psi x equal 0. So the psi x 0 means, but we know that our particle is inside the box. It means the psi x will be non-zero, but you are getting the psi x equal 0. Therefore, it means the A will be non-zero for the acceptable solutions. Okay, so it means A will be non-zero. So if A will be non-zero, then definitely the second this condition B, it means A is non-zero, and then so sin Ka will be 0. Okay, this term will be 0 because this cannot be 0. So if the sin Ka equal to 0, if sin Ka equal 0, it means the Ka will be n pi. Okay, so the K value will be n pi by A. Let's say equation number 2. So an n will be vary from the 1, like this one, 2, 4, 5. So this is the value of the K. So if I use, if put equation 9 and equation 6, so what we get? We get psi x equal A sin, so n pi A, then x. Okay, so this is, let's say, equation number 10. But for getting the exact wave function, but still we don't know what is the A here. So now our objective is to get the value of the A. What is the value of the coefficient A? So for getting the value A, we'll use the normalized condition. It means probability of finding the particle between 0 to A will be 1. Okay, so if I use, so wave function this one, and then this is real function, so psi star will be same. So if I put the value here, psi and psi star, then what I will get? Then I will get the 0 to a, and then a square sin square n pi x divided by a dx equal 1. Okay, so I will get this condition. Now a square is the constant, and then 0 to a sin square n pi x divided by a dx. Okay, so now I will use this one, the sin square theta equal to 1 minus cos 2 theta divided by 2. I will use this formula here to integrate this function. So a square 0 to a, then I will get 1 minus cos 2n pi x a and divided by 2 dx. Okay, then a square 0 a and 1 by 2 dx minus a square 0 to a, then we will get cos 2n pi x divided by a the dx. Okay, so if we calculate, then we will get the 0 value of this integral, and this all are equal to 1. So I will get only the non-zero term, this one, and so I will get the a square by 2 and then x 0 a, so a square by 2, and then I will get the a minus 0 equal 1. So a square divided by 2 a equal 1, and this gives you a equal 2 by a root. Okay, so now we know that what is the a value. A is the root 2 by a here. That's equation number 11 here. So if I put the value of the a in the equation 10, so then I will get the wave function psi x is the root 2 by a, and then sin n pi by a x. So this is the exact wave function for that quantum particle. Okay, so this is the wave function for the quantum particle. So now if I use this wave function, and then let's say, so now we know that the n value is the varying from 1, so its value are the 1 2 3 4 5 6 7. So for the n equal to 1, then if I write the n equal to 1, n equal to 1, I will get the psi 1 x, that will be root 2 by a sin pi x by a. Then for n equal to 2, then I will get psi 2x will be root 2 by a sin 2 pi x a. Similar for n equal to 3, then psi 3x will be root 2 by a, then sin 3 pi x divided a. Okay, similarly we can get for the other value of the n here. So if I plot, and then this is the wave function, so the probability density is, let's say, defined with the Pn with the psi n star psi n. Okay, this is the probability density. So for n equal to 1, we will get the, for n equal to 1, P1 will be psi 1 star psi 1. For n equal to 2, P2 psi 2 star psi 2. For n equal to 3, and P3 psi 3 star psi. Similarly, we can also calculate for the other value of the n. Now, if I plot the value of this one, the wave function for this particle here, I plot the distribution of the wave function. So let's say this is our the potential the way here, x equal to 0 and then x equal to a, and then let's say this representing the n equal to 1, then this is for the, let's say, n equal to 2, and this is for the n equal to 3. So if I plot the wave function, okay, so this is the distribution of the psi 1 x here, and then this is the center of the potential value at x equal to 2, and then we plot, then you will, this is the plot of the psi 2, and if you go for the psi 3, then this one. So this is the psi 3x. Okay, so these are the wave functions in the potential value for that particle for the different n value. So now if I plot the probability distribution of the same particle in the potential value, so the probability distribution, so the same the potential value here, 0 to x equal to a here. So let's say this is for the n equal to 1, and then this is for the state representing n equal to 2, and then this is the n equal to 3, like this, and other states. So this is the center at x equal to a by 2. So if you plot, then we will see, so this is the plot for the P1, and this is the plot for the P2. Similarly, this is the plot for the P3. Okay. So what we conclude from this, these the probability distribution plots. So in the ground state, which is corresponding to n equal to 1, so we see the probability of finding the particle will be maximum at x equal to 2, at x equal to a by 2. It means at the center of the potential well, and for n equal to 2, we see the probability of finding the particle is maximum at this point, and at the center it is 0, and then at maximum at this point. And for in this state, the probability distribution will be like this one. It means the probability of finding the particle maximum, and also maximum here, and also maximum here. Okay, so we are getting the n minus 1 nodes inside the potential well. So now the question is, what is the energy? What is the energy spectrum of the particle in the same potential well? Okay, so we earlier defined that k square equal to 2mh cross square e, and then we got the k value n pi by a. Okay, so if I do the k square, k square will be n square pi square divided by a square. Okay, so let's I takes the both equation a and b. If I compare, both are the k square value. So if I compare, then what I will get? I will get the 2me h cross square is equal to n square pi square a square. Okay, so from this we can get the e equal n square pi square a square h cross square 2m here. So this is for the another state, so we can also I can the n here. So the n square pi square a square h cross is the s by 2, so I will write the h square 4 pi square and then 2m here, so pi square, then I will get the n square h square a square then 8m, or I can write the en equal n square h square divided by 8m a square. So this is the energy of the particle in empty state. We know that the n equal to 1, 2, 3, 4. So if I write the energy of the particle in 4 different times, so I know that En equal n square h square 8m a square and 4 n equal to 1. We will get the E1, that is equal to the h square 8m a square, and for the n equal to 2 we will get the E2, that will be 4 times of E1, and if n equal to 3 then E3, that will be equal to 9 times of E1. Similarly n equal to 4, E4, that will be 16 times of E1. Okay, so these are the energy of the particle in the potential well. So if I plot the energy spectrum, so let's say this is representing the n equal to 1. So the energy of this one is the E1, and then this state, let's say it is the N2, then energy is the 4 times E1, E2, and then this is the n equal to 3, then energy equal to 9 times of the E1. Similarly, we can get the other values also here. Let's say this is n equal to 4, and then we will get the 16 times of the E1. Okay, so what we conclude from here, the energy of the particle, quantum particle, the energy of the particle is the quantize of the quantum particle is quantize, because we are not getting the continuous energy spectrum, we are getting the discrete value of the energy. Okay, and the energy value are discrete. Discrete in nature. We are getting the discrete value of the energy for the particle. Okay, so these are the energy value of the particles. But now the question is that why we are not taking n equal to 0? Because we know that the psi x equal to 2 by a psi n pi x divided by a. This is the wave function for the particle at x position inside the potential well. So let's say if n equal to 0, then what I will get, the psi n 0 will be 0. So I will get the psi x will be the sign 0. Okay, so sign 0 is the 0. So we will get the psi x equal to 0. So if I consider the n equal to 0, then I will get the psi x equal to 0. But psi x equal to 0 means the particle is not inside the potential well, but that is not true. Okay, so but for our case, for this case, particle is inside the potential box. It means there will be the probability of finding the particle inside the box. It means the wave function will be non-zero inside the potential well. Okay, so therefore the n equal to 0 is not acceptable. Therefore we are taking the n equal to 1 a minimum value. Now if the particles is a wave, it look like a wave inside the potential well, means we know that this is the wave function. So we got the different distribution of the wave functions here for the n equal to 1, for n equal to 2. Okay, it means these are nothing but these are the wave. These are the waves. It means this is the quantum particle. So the particle is behaving like a wave here. So what will be the wavelength? Wavelength of particle. Because it's behaving as a wave, then what is the wavelength of the particle? So if we calculate the wavelength of the particle, so what we know that, so wavelength of the particle from de Broglie wavelength relation, we know that lambda is equal to the p, one relation, and we also know that the lambda is the 2 pi by k. So I know what is my k value. K value is to n pi by a, for n to 1, 2, 3, 4 like this. Because if I put the k value, this k value here, then what I will get lambda. Lambda will be n pi, then a here. So I will get the 2a divided by n. Okay, so the lambda 2a by n. So for ground state, it means for n equal to 1 state, the lambda, let's say is I can define the lambda in here. Lambda 1 will be 2a, for n equal to 2, lambda 2 will be a, and similarly for n equal to 3, lambda 3 will be 2a by 3. Similarly, okay, we can get the other values of the wavelength for the particle. Now the question is that what is the minimum energy of this particle? What is the E minimum of the quantum particle? So let's say we know that for the classical particle, E minimum could be 0. Okay, so for the classical particle, if we use if we treat the particle as a classical particle, or in the classical mechanics, the minimum energy of particle could be 0. Okay, and then the maximum we can get from the mv max square here. So from this one we will get the v minimum will be 0. Okay, so classically the particles can have the 0 velocity, and then maximum energy will be this one. So the energy spectrum will be continuous. Okay, so if I consider this is the classical particle, then definitely the energy of that particle will be the continuous spectrum. Okay, so it means we will not get the discrete energy spectrum for that particle, and then particle can have the minimum velocity 0, or we can say the particle can have the minimum velocity 0, and the energy is also energy is 0, and then velocity is also 0. Okay, so suppose that this is the case. This is the case. So if I consider v equal to 0 for this particle, let's say the particle, this particle is in stationary state. Okay, then the minimum velocity of the particle is 0. Let's say I assume for this quantum particle, then lambda h by p from the de Broglie relation, then I will get the h mv. Okay, so lambda will be h divided by mv, then v0, so I will get the infinite. So lambda will be infinite here. And so lambda is infinite means, if I consider, so this is the potential value here. Then let's say I taking this is the lambda 1 for the, so in the real case I am getting this is the lambda 1. Whatever the distance, the lambda 1 is the 2 times of the a for this n equal to 1 state. So now if the particle having the velocity 0, it means lambda is infinite. So if I consider now in this case, what will I get? So I will get now the wavelength will be the infinite. So maybe we will get the very large wavelength here. Okay, so we will not get the nodes at the point at x equal to 0 and x equal to a. Okay, it means, but in our case the lambda is the finite. But if the particle is stationary, then we are getting the lambda is infinite. It means the lambda is not possible. So it means the v will be non-zero always. Okay, so it means that the quantum particle will never stop in the potential value. Okay, so its velocity will be always the greater than the 0. So in this case, so E minimum will never be 0 for this particle, this quantum particle. So I will get the E minimum will be some finite value. Okay, and that finite value of the minimum is the E1. E minimum is the h square, then 8m a square. So this is equal to the E1. Okay, so the E minimum is the E1. So this is the minimum energy of the quantum particle. Okay, it means, so the classically we got the two differences here. If we consider this particle is the classical particle, and then if we consider this is the quantum particle. So in the classical particle, we will get the energy, this energy spectrum should be continuous, and for the quantum particle we are getting the discrete energy spectrum, as well as E minimum is the non-zero here, and then discrete energy band, and here is the E minimum could be 0. Okay, so this is the major difference between the classical approach and then the quantum approach to the particle which is confined in the potential. Thank you.